Okay, so I just would like to continue with the issue of calibration. Let me check what's the best solution. Okay. Is it okay? Not much light. As I said, I would like to continue with the issue of calibration on rainfall of models. I get back the PowerPoint presentation. Visualization is not optimal. Okay. So again, let me go back to the issue of model calibration. I just remind you that calibration is the process of tuning the values of the parameters, of the model parameters, in order to optimize model performances. And I just would like to remind you that parameters are constant or variables that are embedded in the model equations, which can assume different values. For changing values of the parameters, we have the opportunity of optimizing the model performances, and therefore parameters ensure flexibility, but by changing the model parameters, we don't change the model structure. Therefore, I introduced to you the issue of calibration, and I mentioned two different approaches, which are manual calibration and automatic calibration. For automatic calibration, I mentioned to you that we have the need to define an objective function in order to put the computer, the code, the program, in the condition of evaluating the goodness of the simulation, the goodness of the fit. And I mentioned so far two objective functions. The least squares, or the sum of squares, is the objective function. By minimizing the sum of squares, you apply the least squares approach. And I also mentioned the Nash-Sutcliffe efficiency, and I told you that basically these two objective functions are equivalent. And I also put the accent on the fact that these are quadratic objective functions, meaning that they put emphasis on the reproduction of the higher flows. They put emphasis on the goodness of the fit of the higher flows. And I ended my last lecture by mentioning the correlation coefficient. There is no need for you to remember this relationship here, because this is an objective function that is not frequently used, but I want you to know that it exists because sometimes it's mentioned by the literature. And basically this is an index that varies between -1 and 1. I'm not providing any proof for this, where good performances correspond to values of the correlation coefficient that are close to 1. Okay. Now I would like to introduce one more objective function, the last one that I'm mentioning, because it's not quadratic, and therefore doesn't put particular emphasis on the higher flows. This gives equal weight, or let's say gives more weight, more emphasis on the simulation of the low flows. And this is called usually mean relative error. It's computed in a very simple way. You see, I remind you that xt is the variable that is simulated by the model. Typically we are talking about rainfall runoff models, so xt is a runoff, a river discharge. X at t is the corresponding, x at t is the value simulated by the model, while xt is the observed value. Okay, so it's the difference between observed and simulated. It's not squared like before, but we just take the absolute value. And then we divide it for a scale parameter, which is the observed observation, which means that this is a relative error. As you see, it's the relative error. And we should say the absolute value of the relative error. In fact, in some texts, you find it mentioned as mean absolute relative error. Would be more comprehensive, more correct. Then, after you took the absolute value of the relative error, you just compute, you divide by the number of observations. So basically, it's the mean, but in order to get the mean absolute relative error, you should divide here by 1 minus n, the number of observations. This would be a scale parameter, because in order to get an indication of the mean, of course, you have to take the summation of all the absolute relative error, but you should divide also by n. So you could put here a 1 over n. Okay, it doesn't change anything for the model, because for the calibration process, because our objective is to minimize this quantity. So the fact that you divide by n or not doesn't have any effect on model calibration, because of course the minimum of this relationship is also the minimum of the same relationship divided by n. So it doesn't take any effect again on model calibration, but if you want an indication of the mean relative error, indeed you have to divide by n. So getting this relationship. F theta. Theta is, I remind you, is the parameter vector of the model. 1 over n, summation from I equal 1 to n of absolute value of xt minus at xt divided xt. This would be an equivalent relationship if you want to obtain the mean value. But again, it doesn't make any difference if you divide by n with respect to model calibration. So again, I would like to stress that this is an objective function that you should use if you want to put more emphasis on the simulation of low flows. So you have seen that we may have different alternatives for the objective functions, and I'm not mentioning all the possibilities. If you look in Google for objective functions and hydrology, objective function and hydrology, you would get a longer list, a much longer list. Of course, we are not interested in analyzing in detail any possible alternative, but there are objective functions that are based on, for instance, on optimizing the simulation of the water volume instead of individual discharge simulation. Because sometimes when you apply a rainfall runoff model, you are not interested in getting a good reproduction of the hydrograph, but you might be interested in getting a good reproduction of the volumes, for instance, like weekly volumes of water delivered by the river, or monthly volumes, because some structures like dams, for instance, need to be designed also basing on the water volume that is delivered by the river. So there are many possible alternatives. And now let's concentrate on the open issues, on the main problems that you may experience in calibration. Because basically, the procedure is not complicated, as you have seen. You have to select an objective function, depending on your needs, on your modeling purposes. And once that you have an objective function, you use an algorithm with the personal computer to get the parameter value that gives to you the best performances in terms of the objective function. Of course, we still don't know how to apply these algorithms. I mentioned to you that we don't need to know in detail how they work, because basically we have a lot of computer packages that gives us alternatives for these algorithms, and so we don't have to care about that. They are well tested. We will see in R that we can use different alternatives for finding the optimum value of the objective function. But still, even if the procedure looks quite simple, there are some classical problems that are experienced during calibration. And let's have a look at these problems. First of all, this is not mentioned here. It may happen that your algorithm fails in finding the optimal parameter vector. So the algorithm, the program, the code tells you that optimization was not successful. This may happen for many reasons. Main reasons are that the number of allowed computation was reached, because in order to put a limit on the number of computation, usually you set a maximum of trials, a maximum number of trials. I mentioned to you that the computer has to try with randomly selected parameter values, and of course the number of trials must be very high, but we have to put a limit because we can't allow the computer to perform billions of trials. So usually we put a limit, usually not explicitly. It's the program that has by default a limiting number allowed for iterations. Another reason could be that the response surface is complicated. Let me make an example, because it's not the response surface, you don't have an idea of what is. So let me make an example. Let's suppose that you have just one parameter, okay? So in this case, it means that the parameter vector theta of your model counts only one parameter. This is the case of the linear reservoir, for instance. Remember that IMOD, for instance, has 5. Usually, hydrological models have several parameters. 5 is considered in hydrology a small number. There are models that count more than 20 or 30 parameters. But let's concentrate now to provide you an example on the case in which we have just one parameter. Then it's possible to plot a graph showing you, depending on the parameter value, showing you the progress of f theta. First of all, many algorithms very often ask you to fix a feasible range for the parameter values. Meaning a range, in this case, is just one parameter, so the range is just a segment on the x-axis, on the abscissa, such that you tell the program to look for the optimal value only within this range. Some codes ask you to provide this specification. This is very much useful because you can limit the number of trials. If you have already an idea based on expert knowledge of the most probable parameter value, this is the opportunity to take advantage from this prior knowledge. So if you have, for instance, an idea that theta may have is likely to take an assigned value, then you give a range around that value, which is as wide as you think it's appropriate, and you can take advantage from this expert knowledge. If you don't have any prior knowledge, any expert knowledge, you just have to allow the range to be very wide. So some programs, some algorithms allow you to specify the range, and this is a useful opportunity. Some other algorithms not, but this is quite a useful opportunity. So let's suppose that you have, again, only one parameter for which you specify the range, and then you can plot the objective function depending on the parameter value. And if you are lucky, the objective function looks like so. Why I said if you are lucky? Because in this case you have a well-defined minimum for the objective function corresponding to parameter value theta star. This is called the response surface. This is not a surface indeed, this is a curve. But if you add more than one parameter, then, for instance, two parameters, you should plot one parameter along the abscissa, and maybe you can plot the other parameter, theta 2, on a second axis on the horizontal plane, therefore getting for each couple of parameters value, theta 1 and theta 2, a value of the objective function. And in this case you would get a response surface, because it wouldn't be a curve anymore. It would be a 3D graph that shows to you a surface. And in this case, the surface can be displayed on a graph, on a 3D graph. If you add more than two parameters, the surface will become a n-dimensional surface where n is the number of parameters. So you have a n-d surface where n is number of parameters. The symbol, probably you know better than me, this is used in American English to identify number. Like we use this one in Italian, and in American English you use this symbol, which is called, I don't remember in English, hash maybe, yes, hash, to mean number, okay? So again, you would get an hyperdimensional surface which cannot be visualized in a graph, but indeed it becomes very much complicated if you have a lot of parameters. But let's go back to the original case of just one parameter. And let's put in evidence that very often you are not so lucky as in this case. You may get a response surface a response curve, sorry, which look like this. So indeed you have a minimum which is here, but it's not easy to find it, because the algorithm can be trapped in local minimum. This is the correct terminology. The algorithm gets trapped in a local minimum, meaning that it starts looking here, and he finds a minimum here, and the algorithm thinks erroneously that this is an absolute minimum, because the algorithm may look in this direction, but the algorithm finds that the surface is increasing, the objective function is increasing, and therefore he may stop to look in this direction because he doesn't have the perception that after a while then the objective function goes down again. So he can get trapped here, inside here in local mean. So this is another problem. There are several types of algorithms, and some of them are more efficient to deal with complex surfaces. Moral of the story: when you apply an optimization algorithm, you should carefully look at the report that the algorithm should provide. Any algorithm, any good algorithm, even those that are embedded in Excel, give to you a report after the algorithm is finished, after you finish the job. Sometimes the report is just one line, like number of maximum iteration exceeded, point, dot. And this means that, of course, you have to be very careful, because he says that he stopped not because an optimum was reached, but because the number of iteration was exceeded. Sometimes the report is much more complicated, tells you a lot of details about statistics of the work that has been done. So my recommendation is try to always have a look at the report. And this is a general recommendation that I would like to give to you. Once that you rely on the computer to perform a computation, and today this happens for almost everything. You use Excel, you use other programs to make computation, even R. Don't assume that the computer is always right. There are good possibilities that the response of the computer is not right, maybe not wrong, but even not right. So you should always be in doubt, especially when you use computer codes that are not well tested. And, but even with well-tested computer codes, there are some bugs, and therefore you have to be always very careful. If you look, for instance, in Google, if you search for Excel and bug, in Google there are some examples of computations for which Excel provides a wrong answer. Even very simple computation, like very simple multiplications. But there are some cases, they are known bugs. Some of them, of course, are periodically fixed. This to prove to you that even a well-tested program, like Excel, can give wrong answers. So you have always to be in doubt, meaning that when you have the possibility to check the report from a program, you should always check it, because the report is always useful to check. But even for, like I'm performing every day a backup of my PC, I try once in a week to check the report of the backup, because sometimes the PC simply says the backup was failed. The backup failed, and if you don't check, you don't get the perception that you assume that the PC is backupping while it's not. Okay? So in this case, again, always try to understand if the optimization was successful. And of course, it depends on the algorithm that you use. And my suggestion is also to get familiar with one specific algorithm and to get familiar with its performances if you need to do very often this kind of calibration procedures. Another issue that I would like to mention, which is not mentioned here, is that usually the algorithm asks you for an initial parameter value, meaning the parameter value that the algorithm should try first. And if you have any, like in this case, any expert knowledge, any prior information about parameter values that are more likely, it's recommended to start the algorithm with such initial value that you believe more probable for the final result. Because this saves computer time, first. And also, you know, the success of an algorithm also depends on how much far you start with your search. If you start very far, the algorithm is more likely not to be successful. If you start close to the final value, to the true value, then the algorithm is more likely to be successful. And as a final recommendation, when you are in doubt about the output from a minimum optimization algorithm, try to run it again with a different starting value. If the result is reliable, then you should obtain the same result or very close results for different starting values. Okay, unfortunately, in many cases, the response surfaces, I say surface in general, in this case it's a curve, but in general, you should call it response surface. The response surfaces of hydrological models are much complicated. And here there are some reasons why they are. The first problem mentioned here is overfitting. What does it mean, overfitting? It means that you don't have enough data to reliably estimate the parameter values for the model. Let me make a very extreme example. Let's suppose that you want to estimate IMOD 5 parameters with 3 observations. You can understand that there is something wrong. It cannot work. Because if you have 5 degrees of freedom, it means that you have at least imposed 5 conditions. This is a minimum requirement. But in hydrology, we often say that the ratio parameter observations should be 1/100, meaning that if you have just one parameter, then 100 observations allows you to get a reliable fit. If you have 5 parameters, then we say about 500 observations. This is just a rough indication to understand what the relationship should be between number of parameters and number of observations in which the objective function is calibrated. Overfitting means that the number of parameters is too high in relation to the number of observations. Overfitting implies that you get very good values for the objective functions, not because you got a reliable fit, but because the number of points that you are reproducing with the model is too limited. Of course, if you have to fit just a few observations, it's easier, it's quite intuitive that it's easier to get a good fit. Instead, if you try to fit 30 years of hourly data, or let's say 100,000 of numbers, of course, the fit becomes more complicated. Overfitting is absolutely to avoid. Therefore, when you select a model, you always have to keep in mind how many observations you are fitting the model on. Now, equifinality. Equifinality is a concept that is relatively modern. Means literally that you have more than one parameter vector providing the same level of fit, equally good values for the objective function. Again, you have more than one parameter vectors, so you have different parameter vectors providing similar values for the objective function. Look at here, for instance, this complicated curve. You see that if you look at the minimum, in this case there is one minimum, but there are also many other local minima for which different parameter values provide similar values of the objective function. This is a quite common occurrence in hydrology. And equifinality is strictly related to overfitting. If you are overfitting a model, then it's it's easier to experience equifinality. Equifinality means equivalence of target. Therefore, equivalence, same value of the objective function for different parameter vectors. Of course, your algorithm cannot distinguish, cannot really, once that the value of the objective function is comparable, the algorithm cannot distinguish between different alternatives. Equifinality is often induced by correlation among parameters. What does it mean? It means that parameter values are correlated. Like, let's suppose that you have two parameters, and like, for instance, in IMOD you have 5, and it may happen that if you increase one parameter value, you get a similar response if you decrease, for instance, the third parameter value. It means that the hydrograph doesn't change much if you take two parameters value, increase one and lower the other, or increase both. It doesn't matter. Meaning that you change two parameters and the hydrograph doesn't change much. This means that the second parameter is compensating the change of the first. Compensation. Compensation among parameters, correlation among parameters, they are similar terms. The meaning is the same. Of course, when you have this kind of compensation, you understand that you may have two different parameter vectors providing similar values for the objective function. So, equifinality is strictly related to correlation among parameters, or compensation. This is typically what happens in hydrology. Parameter values are correlated. For instance, in IMOD, you may find that the maximum water storage Cmax is correlated to beta. If you change one, you may compensate the change by changing. If you change Cmax and you increase Cmax, you can compensate the change by decreasing beta. Now, there is the problem that how to solve these calibration difficulties, how to be able to distinguish between two parameter vectors that are equifinal. And this is an open issue. The scientific literature is still discussing about methods that can be used to resolve equifinality, to resolve overfitting. You know, overfitting is you just have to minimize the number of parameters or increase the number of observations. But for resolving equifinality, you know, it's still a problem that the literature is discussing. Basically, the main idea is to increase the amount of information. When you estimate the parameters of a model, when you calibrate a model, you are using some information, which is basically observed data. So the suggestion is try to increase the number of observed data, either by collecting more data, but this takes time, or by using some alternative information in calibration. Like, for instance, instead of using only the hydrograph, instead of just matching the hydrograph, some people try to estimate the soil humidity, the soil water content, and match both hydrograph and soil water content. Because when you use IMOD, for instance, you get at any time step an estimate of the volume of water that is stored in the basin. And so you get an estimate of how much you are close to saturation, how much your water stored in the catchment is close to the maximum. And therefore, if you get an estimate of soil moisture, soil humidity, then you can use these estimates of soil moisture to condition the model, to match the soil water content that is expressed by IMOD. This is an idea. Of course, it's an idea which is not easy to put in practice because, you know, to get a reliable estimate of soil moisture at the catchment scale is not easy. But today, we are more lucky than in the past because we have the availability of new measurement techniques like remote sensor that allows you to get indeed an estimate of soil moisture based on satellite images. So if we had an opportunity to use this kind of information, this is of course very useful because you may find that two parameter vectors that were equifinal with respect to the reproduction of the hydrograph, you may find that they are not in the reproduction of the soil water content. Therefore, you can get an indication to distinguish their performances. And also, I would like to make clear an issue because you may wonder why do I need to distinguish. You may think, for instance, that if two parameter vectors give equally good simulation of the hydrograph, you may think, who cares? I take one or another because the performances are similar, so I don't care about identifying the one that is more true. I just care about the goodness of the fit, and if the goodness of the fit is comparable, I don't need to distinguish. This is not correct, because we are talking here of calibration. And calibration is basically an interpolation of observed data. You get observed data, and you find a mathematical relationship to interpolate them. Okay? This is interpolation. But when you use the model to predict a future situation, or a situation that is not comprised in the calibration procedure, you are extrapolating. This is a different story. Okay, so if I calibrate a model, I calibrate the model, why? Because I need to use the model for simulating data, in our case to generate synthetic series. Therefore, calibration